which would like to actually end on a high note again with another keynote, with a keynote talk. Today is going to be the last speaker. The last keynote speaker is Jason Teutsch. He's a mathematician, computer scientist, and his research background includes distributed systems, compute and game theory, and algorithmic randomness, and security, and of course, blockchain. He has held a postdoctoral position in institutes such as the National University of Singapore and Penn State and other places, and also research positions in think tanks like RAND Corporation and IDA. And he has been, I think his main, one of the biggest achievements has been the founding this Truebit, a company that he's the founder of, and it's providing a scalable, verifiable computation. So it's an off-chain computation that off-chain of Ethereum that provides this scalability and verifiability for computation. So thank you very much, Jason, for accepting our invitation, and it's given to you.
Thanks, Ray. Thanks so much for having me. It's really a pleasure to be able to give this keynote at BTS 2022. As it turns out, I broke my collarbone last week. So I would first like to express special thanks to everyone who helped get this talk across the finish line, Mark, Josh, Kelly, and of course my dad, who in the 11th hour helped me get this computer on the desk. So as we can see, I think everyone can see my slides. The theme of this talk is nec pluribus impar, which roughly translates to not unequal to many. It's also the name of a notable blog on a related topic. And on behalf of Truebit, we are going to now face off against a pile of chocolate. So let's get started. Yeah, so as Ray mentioned, I founder of Truebit. Usually, so let me say what we're not going to be talking about today, which is scaling Ethereum. Even though Truebit was one of the very early scaling projects in the blockchain space, the story for Truebit began with the verifier's dilemma, which explains why Ethereum needs a gas limit. We predicted that, months before the network launch, and then really the motivation to build Truebit was creating a two-way peg, or sometimes known as a kind of decentralized bridge between Dogecoin and Ethereum networks. And of course, the point there was that we needed a way to check Dogecoin proof of work inside of an Ethereum smart contract, which is sort of beyond what native smart contracts would be able to do in Ethereum. But as I said, we aren't going to talk about Ethereum, but for those who are familiar with Truebit and came here to learn more, your patience will be rewarded. I would say, especially for those of you who are logicians like myself, who did my PhD in mathematical logic. In this talk, we are going to take a Platonist view that certain objects are really out there. For example, in mathematics, the natural numbers really exist, but we as humans only comprehend them through the formal language of mathematics itself. And in this talk, we'll witness some ground truth instances through the lens of formal processes. So I hope the analogy is clear. Let's get started with our first viewpoint. So here is an example where people see different things. Let's now break this down in the form of a definition. So what we could see is in the video, two different people who saw two different things. Well, we can sort of formulate this in terms of with a river analogy being upstream and downstream. So we say that a downstream shadow occurs when one lacks visibility into upstream processes. So upstream, there are these real events that occur somewhere in our universe, and downstream, we somehow perceive them. And therefore, you can understand a shadow as being a kind of uncertainty about an upstream state or an upstream action. It's also an impression of reality. It's not the reality itself. So I would now illustrate this with a simple example of air traffic control. So here we have a plane. The plane is a form of ground truth in that at any moment in time, it has a specific position and a specific velocity, which is actually happening in the world somewhere. And before that, I just put a warning here that flying planes is dangerous. Obviously, they collide into something, you can get serious damage. So it's very important to do it carefully. And there are specific air traffic controls, if you're coming into an airport, that help to guide these planes carefully. So an air traffic controller obviously doesn't directly experience the location of this airplane. There are certain sensors that it uses to track the airplane. So you have GPS trackers, maybe you have radars, and they measure the plane within, the sensor would like to get the exact position of the plane, but it has physical limitations. And then, you further interpret these sensors in a kind of mathematical model. Typical model is the Kalman filter, which inherits these, inaccuracies downstream. But that is the whole point of a Kalman filter. It handles unreliable sensors due to their lag, due to the inaccuracies and precisions of those measurements. And in fact, the model reconciles sensor history using a recursive state estimator based on what it's seen in the past. It's able to predict position and velocity based on its prior state observations, and of course, certain assumptions that are made into the model as well. So now let's tie this back into our definition from the previous slide. Here we see upstream process, which is the plane that's actually out there flying around, our ground truth with position and velocity. And downstream, we have the sensors that obtain some sort of shadow of the plane's experience. And on top of that, the Kalman filter now reads those sensors downstream again. And so it's a I guess you can say a shadow of a shadow, a double shadow. And of course, the Kalman filter is feeding back into itself. So you could see this mark of internal state that comes in and helps it to predict the next state based on predict the current position and velocity of the plane based on all the previous measurements that were taken from the sensors. And of course, I should point out that if we could know exact instantaneous airplane position, then the downstream view wouldn't have a shadow at all. And clearly, in the case of blockchain, there exist sensors for Ethereum price, but these two have limited accuracy and precision, especially during periods of market volatility. So this is very relevant to the blockchain. So now let's take a look at our first example here of an explicit blockchain shadow. So in order to experience the blockchain, one requires a lens. So you need, this lens is a kind of client for which to, I guess, experience the database. So here we have examples of two different lenses. One is called Etherscan, the other is called TrueBlocks. And each of these lenses gives us different information about the history of a particular address. This might sound a little bit surprising because the theory of blockchain tells us that the blockchain is a universal ledger. It's the thing that everybody has consensus on. It's all in common. But in practice, a distinct interface is going to give different results. So let's see this in practice.
We get to a total of 231 total transactions. Now let's go back to TrueBlocks and see what it says. it says there are actually 210 transactions. What's the difference? This is something we've looked at pretty carefully. In fact, we recently published a Medium article titled How Accurate is Etherscan? The upshot is Etherscan duplicates records across the 4 different transaction types or tabs. When we remove the duplicates, Etherscan actually only has 196 transactions. So there's still a difference between Etherscan and TrueBlocks. So what does this mean? Etherscan, as it turns out, is missing transactions. We've started.
Okay, so as we can see, we got different views for a specific address. We saw a different list of transactions for a specific address based on the client that was chosen to be used here. So let's look at some other blockchain interfaces. So on the left-hand side of this slide, we see a view of Ethereum from the original Geth client, which is still the way that miners, interact with the blockchain today. On the right-hand side, we see the way that most people experience the blockchain, which is through web browsers, or I guess websites behind those web browsers and their extensions. So in the first two items, we have OpenSea and Rarible, which are non-fungible token marketplaces where you can buy and sell tokens. I already gave a great introduction to NFTs this morning, so I'm not going to go into much depth there. The third category of I guess browser experience here is MetaMask, which is a browser extension, which is what one uses to interact with these sites that are connected to Ethereum, so that you can, for example, execute a trade that gets recorded onto the blockchain. All right, so let's now illustrate some of the danger of flying objects. In this case, maybe a digital object, but here it's and a different kind of danger. But going back to our plane analogy. So Moxie Marlinspike, who is the founder of Signal, he posted an image on a website and assigned its ownership to an NFT. Okay, and when you viewed this NFT on OpenSea, could somebody mute their mic, please? When you viewed on OpenSea, it looked one way. So here's how his NFT looked on OpenSea, and when you looked at it on Rarible, it looked different. And of course, if you went to the actual website where he posted the image himself, you would see something even different from those two, which is, there again, our pile of chocolate coming into effect. And oddly enough, when Moxie went to access his NFT, this NFT from his own wallet in MetaMask, he got this error. It says the item you tried to visit is no longer available in OpenSea. I'm sorry, I left out an important detail here, which is that OpenSea actually decided to remove Moxie's artwork from the platform. And at that point, he lost visibility of it in his MetaMask wallet. In fact, he said all the wallets in his computer, and he and that's what this error message is here. So what we can see is that, yes, when MetaMask is actually, in order to get MetaMask's view of this NFT, it's making a query to OpenSea. So when OpenSea, I guess, decided to change their view, then that affected MetaMask. So we're seeing sort of a centralized client accessing to another client upstream. But it gets even more interesting than this. So there's actually a third layer of centralization, which we can capture in the following, what I call syllogistic paradox. So let's start with the facts. First of all, axiom 1, convenient downstream system views require server interfaces. And those server interfaces require centralized dependencies. And now using the property that the word require is transitive, we can conclude that convenient downstream system views require centralized dependencies. A fortiori, number 3 holds if it's true for all systems, true for decentralized systems, including views require centralized dependencies. It's a bit strange, and if we sort of take this to our something still like that here in green, which is blockchain application intentionality. And really, when MetaMask is making a call from through a Web3 site, that site is being delivered through a service called Infura, which is a centralized service which reads the blockchain and feeds it into the MetaMask extension. There's another one here called Alchemy, which is used similarly for other blockchain applications. But generally, most web applications are either using one or the other of these two services. So essentially, in order for most people to access the blockchain, you're reading in data through a centralized server. And I know some people might disagree, but I think Ethereum was intended to be more than just storage for an Infura web server. And I guess just remember here, we're not talking about interactions. It's not how do you send a transaction to the blockchain to Infura. It's how do we get a view of the blockchain? So any of those statistics or whatever that are coming up and being shown to you through the website are those are being fed through on the server. So I guess I leave with this slide with a thought, if an NFT falls in the woods and Infura doesn't hear it, does it make a sound? Okay, now let's see when things get even a little bit worse, I guess. So I'm calling this when shadows become blackouts. So as the first bullet here says, native smart contracts lack upstream visibility into complex computations. So indeed, Ethereum smart contracts don't see data outside the blockchain because the mining software doesn't permit it. If you're running a mining software, it says verify these transactions, and it doesn't say, go look on other websites for data. So essentially, the outside data is completely blocked to the smart contract. So this is what it's called an absolute downstream shadow or a blackout. And what we're doing with Truebit, a way of viewing the Truebit technology is a way of increasing visibility for smart contracts. So you have a DApp contract that basically, it can't see complex computations, doesn't see the data, but it wants to evaluate a function on some, let's assume some larger inputs. So it takes a function f, it takes its inputs x and y, sends these out to a Truebit contract. The Truebit contract should call back with f evaluated at x and y. And what I want to show in the next few slides is how Truebit actually gives you visibility into why, to basically prove to the smart contract that this is correct by increasing its visibility into that process of computation. Now I know this is kind of we're here very blockchain specific, because in the real world visibility is not as black and white as it is with smart contracts, and we'll see later that it's actually possible to have two incomparable views in the real world, without basically just you don't have just a blackout, but you could have sort of two incomparable shadows. Let's say it that way. Okay, so let's take a look at how Truebit provides this kind of visibility. I'm calling this unanimous downstream consensus. So essentially, when a computation is being done, a solver will perform. Let's say a solver performs this computation. It says, okay, I got your function f, your inputs x and y. I think f of x, y equals 12. And some verifier comes in and says, I don't agree with that. The solver says, let's play a verification game, which essentially means the solver is taking, or the solver and verifier are going to court. Who's sitting in the court but the set of Ethereum miners who actually are essentially, they are the smart contracts on the network. And the assumption here is that miners are always right, but they have very limited computation bandwidth. So what they're going to do is force the solver and verifier to play this verification game to sort of figure out exactly where they disagree in a way that doesn't require the judges to, I guess, consume a lot of computational bandwidth, which they don't have. So how do they pinpoint this disagreement? So essentially the solvers and verifiers are going to enumerate their computation states off-chain, and the judges are going to enforce binary search. So that's just a simple heuristic. So we have here a list of all the snapshots of the computation that happened with the solver. Clearly, because of the definition of the task, they have to agree on the initial state. They didn't agree on the final state, or they wouldn't be sitting here in this court. So the solver says, do you agree with my snapshot at time n/2? The verifier says no. So we have to go closer to the beginning of that computation. So what about n/4? Yeah, that looks okay. And what about, so then we move more to the right, 3n/8. Eventually you keep slicing and dicing and you get to a step which is small enough that the judges can actually execute those on chain. And of course, very important that these computational steps are identical across all the platforms in order to rule fairly on the final check. Obviously, if they're going to be different, then you have no way to compare them. So let's take a look at how this final step works. Here again, you can see the on the right-hand side, the green where they agreed, the red they disagree. So the solver is saying I started in this green state, I got to this red state. This is supposed to be a representation of the machine state. I've sort of represented it as an abstract Turing machine, and the way that it's actually stored is this Merkle tree, so that we just put this root on chain to save space. But the solver is saying, okay, I'm a Turing machine. My machine head's in state 0. I see a 1 written on the tape. That tells me to change to state Q1. So write a 0 and move to the left. And the judge says, well, that doesn't look quite right to me. I actually think if Q0 sees 1, you should have written a 1 and changed to state Q2. Oh, I give you that they both move to the left, but clearly these computations have diverged. So the verifier's challenge would be justified in this case, and if there are economics tied to it, then the deposit of that solver would be forfeited. Okay, and of course the important thing is that all these states, the reason we're able to get it is because everything through this process is written on chain between the verification game and this final state, which is actually run by a smart contract. It's small enough. Okay, so for the next example, let's take a look at Truebit in a very practical situation. So I'm going to talk about dark pool settlements. So dark pools are useful for placing large orders that could potentially move a market. So often these are done on OTC desks. One problem with the dark pool is that the lack of transparency can lead to conflict of interest for a pool operator and other parties. So this includes all the elements that we see on this page: the users who are putting in the orders, the pricing providers who are maybe giving the benchmark prices, and the settlement parties who are actually, moving the users' funds between different parties. So the whole point is that the dark pools, the goal is to obscure the buy-sell order book so that that information isn't revealed to other people outside of the parties that would be wanting to execute that trade. And the issue of this lack of transparency is what we call it results in a kind of attack which is called front running, which means trading based on insider knowledge of a future transaction. If you have additional information about the market, you can make moves that can be financially advantageous if other people don't know about them. And of course, any of the parties involved here can do front running, whether it's the OTC desk from the trader who says, okay, I know a big sell order is going to happen. I'm going to trade accordingly because I know the price is going to move. The platform itself could rematch, match the orders in different ways. But the whole point is this order book upstairs is in a dark pool that it should be invisible to everybody, not just certain parties, that gives all of these people the assurance. So it's good, right? I mean, if everyone believes that this orders are going to be executed correctly, they have the assurance of that correctness. They don't need to see the order book. They don't want anybody to see the order book. So in this case, what we're seeing, to translate this into our language up until now, the order book is our upstream event that's sort of really happening. And downstream, you have this assurance, which is a shadow. And everybody wants a shadow because it's beneficial. It makes the dark pool work correctly. So the point here is that this little bit of visibility that you get, from this, by executing through Truebit, obviously there's cryptographics involved here as well. The visibility prevents gaming. Okay, so let's look at another sort of similar situation where we get complete block from upstream data. So this is the area of quantum computing. And so I'm going to explain why it's simply blocked. So you see up here, some of you may recognize this quantum algorithm. That's your classic quantum teleportation. And so a lot of times in quantum computing, this is a relatively simple example. Quantum computing simulations can be very resource intensive. In fact, I call it here resource prohibitive. The local reproduction of a quantum computing simulation, especially on a classical computer, is resource prohibitive, which can result in unverifiable results, in the sense that if you're a graduate student, you see someone that claims a result. In order to reproduce the result, you need 20 computers running over the course of 3 months. You may not have the resources to it. So in essence, that you have no visibility into that computational process. So I would say that complex simulations then lack downstream visibility. So it's just simply a block. On the other hand, if we were able to generate these downstream assurance, like we saw on the previous slide, that would enhance the quality of publications because they're now sort of verifiable, and therefore collaborations as well, because I know I can, sort of have confidence in using the upstream results downstream. Okay, so here is, I'll tell another story, which comes from Jerry Cuomo. This one, credit to Alon Cohen for this one. Jerry Cuomo told the story. He says, suppose you have a machine learning model that exists to dispense medical advice, okay? Now a doctor feeds patient's diagnostics into the model, and lo and behold, the model recommends a drug produced by a pharmaceutical company that also happened to have trained the model. So should the patient's physician find this advice credible? On what basis can or should the patient assess its credibility? So this is let's frame this question in terms of sort of a generic machine learning pipeline. And there's basically 3 roles, right? You have data collection, wherever the data you're using to sort of train your model. Then you have the actual training itself. In this case, the pharmaceutical company happened to have done both the data collection and the model training, unbeknownst to the doctor who is producing the the consumer inference. So if we sort of unpack this into the language that we started at the beginning of this talk, which is the language of upstream, downstream, and shadows, we see incomparable views of healthcare data, which is interesting. So let's unpack it for a minute. So when we're getting the data, getting training data, whoever collected the data has visibility into how it was connected. They collected it themselves, presumably, but anybody who uses that data downstream is just seeing a shadow of the data. They get the data, but they don't have like a record of how it was. I mean, they don't actually experience the collection itself. On the other hand, the person who's training the data, so you have a model, what you're feeding into that model was if you're updating the model based on the training data that's coming in, you have an old model that's coming in, you're inheriting this shadow from the training data. So at this point, what we can see is that well, first of all, the training data provider has no visibility into the model training process because it doesn't maybe see the old model. On the other hand, exactly the opposite. The model trainer has no visibility into the training data collection process because, well, it just gets the data. And the one that's in the worst situation is this consumer that has no visibility into either one of them. It doesn't know how the model was done. It doesn't know how the training data was collected. And yet it's using this to do a kind of classification for itself. And this is a problem because bias can enter at any stage and is not necessarily apparent to the downstream users, right? So, and people using this, for example, the doctor, are not necessarily aware of the biased samples. So, and indeed, these models can be created by individuals or institutions that have conflict of interest of one kind or another, as we've illustrated. So, incomparable shadows, great. Let's look at our last example here, which is about a pandemic called COVID-19, which also took place in Florida. So this is Florida's response to COVID-19, the chief data scientist, okay? Rebecca Jones, who built the Florida State COVID-19 dashboard, says she was fired May 18th, 2021, after refusing to manipulate COVID-19 data to justify reopening, as this reported by Chris Broussard in the USA Today. Now, are you reading this quote, or are you reading this article? Can you tell whether she actually refused to manipulate COVID-19 data? Or is there something else going on? In any case, what we see here clearly is that there are distinct shadows for upstream pandemic events. So what happened after she was fired? Rebecca went out and opened her own website. So there was a Florida dashboard, Florida Health, which reported the official COVID-19 data for the state of Florida. And then Jones created her own website called floridacovidaction.com, where she put what she said was the real data, right? And so interestingly enough, we see here upstream, there was some real pandemic events. Maybe you can even say that there were some real statistics, the data, that there were some actual things that happened in the pandemic that were objectively measurable data that's sitting upstream, and yet downstream you get two, I guess, very different views of those upstream pandemic events. And in fact, if you want, you can, and you live in Florida, you can vote Rebecca Jones for Congress, elect science. And that's actually from her website as well. So it's just hard not to include it. So now the question becomes, finally, what really happened here? So what we're going to see here on the left-hand side, you can see the police body cam video that's outside Rebecca Jones's house. Oh yeah, so this is a few months later. The police actually came by, raided her house, I guess, ripped out the computers. So yes, this story, the plot thickens here. But when you see a body cam, and when you're watching this body cam video, which is actually quite long, there isn't that much happening. The police walk around, they chat with the neighbors, but then there's a moment when they actually reach Rebecca's front door. And Rebecca had her own camera set up inside of the house. So you can see, I'll just play them both at the same time so you can see what happened.
Come outside. Outside. Who else is in the house, ma'am?
My 2 children and my husband.
Where's your husband? Calm down. Calm down.
You want the children down?
Calm them all down.
You want me to do that?
Come down the stairs. Now. Come over here. Police, come down now.
Do not point that gun at my children.
Rebecca.
He just pointed a gun at my
Rebecca.
children.
Just stay right there.
So sometimes it's as important what you don't see as what you do. Obviously, on the right-hand side, we saw a gun. On the left-hand side, we didn't. So in any case, again, 2 different views, exactly the same moment in time, the same place. And I would say lack of consensus, right? So now let's talk about how we can get a viewpoint consensus. I'm going to give this a name, which you're going to call distributed trust. And we have a simple equation here. Distributed trust is provenance plus execution. So first, what's provenance? I'm going to say provenance just means a visible and immutable record. And what it could be a record of lots of different things. It could be the contributor ID that created the record. It could be a record of some sort of ownership, like with an NFT. It could be a compute process, like with Truebit. It could be a timestamp, a data source, a manufacturing step that you would see, for example, in what we saw in the supply chain talk earlier. And this provenance concept has been used exactly in this form in many different blockchain projects. For example, Factum, which said, okay, I have a fact, I'm going to record it's true. It's permanently recorded onto Bitcoin. Provenance, IBM Hyperledger, which is also sort of more focused on supply chain stuff. But the fact is that most of these platforms today are largely non-active. And why is that? Well, one reason might be this lack of execution. So it's not just writing on the blockchain, but also, what was written. So let me say, so I guess the question is, what is execution? Is this the missing piece? So calling execution just means evidence of process correctness. Okay, so there are different ways that one can get evidence of process correctness. One is you just simply do the process yourself. So this means, for example, you're running a task on your local laptop, you did it yourself, and therefore you evidence to yourself it's correct because you did it yourself. It's self-explanatory. Another way to do it is this mode of zero knowledge proofs or secure enclave attestation, where you ask another cloud computer or another machine to perform an operation, and then they give you some sort of certificate that proves that they did it correct, which should be obviously easy for you to verify. And then you have another kind of evidence that a process correctness, this certificate. And then the last way that you could do is sort of, this is more of I guess a physical interpretation, but I call it postal mail delivery. If I open up my mailbox and I pull out a letter, that's evidence that the postal delivery service operated correctly, just because of the fact that I have the letter. If the letter had appeared in my neighbor's mailbox, that might be evidence that it didn't operate correctly, or if I didn't see it at all. So these are different kinds of evidence that you could have. And of course, we can distinguish provenance and execution. So I give this example of income taxes. You want to try to reconcile your income taxes through a public website. For example, we looked at Etherscan in the beginning. We saw that this doesn't necessarily allow your account to reconcile. So you get, in this case, you do get provenance because it's a website, but it's not necessarily execution. I mean, in fact, you might not even get execution either, because the sort of historical prices might not even be fixed, for example. So that also happens. The other way to look at the income taxes is that you would reconcile them locally. You hand wrote them onto a piece of paper. You know it's correct, but the IRS lacks visibility into your process. So this is what I would call execution, but not provenance. And lastly, last definition that I'm going to throw out here is the idea of a centralized server. So a centralized server is a server which is either missing provenance or it's missing execution. So not provenance or not execution. And the justification for this just is an argument by cases. So either you control the server or someone else does. So if you're using if you control it yourself, it's your laptop, this garners execution for yourself, but that's not provenance because nobody else can see it. On the other hand, if you do it on the cloud, this is sort of an obscure upstream process, and it's sacrificing the execution. So yes, you might get provenance because it's served by a web server, but it's, you don't have the visibility into the execution. So I say in distributed trust, no one owns the server. That's sort of the name of the game. And so what we can conclude here is just by putting together these last slides that the opposite of distributed trust, we put a negation in front of the definition of distributed trust, we end up with, well, exactly what we had on this previous slide, which is the meaning of decentralized server. And you can see that by distributing this negation, you get an equivalence in these truth tables. So they really are somehow connected. And in the last moments of this talk, I'd just like to talk about, what are we going to do about this? So neutralizing shadows. There are a few ways that we can sort of offset these downstream shadows. One method is to increase visibility and insurance for server processes. That's sort of what we illustrated with the Truebit example that we had earlier. As an example of method one, remember what we did with the dark pool, we provided assurance, a kind of visibility upstream. Another one is to say, okay, just run the centralized portions yourself. This is what basically what TrueBox does. There's another, I guess, enhancement of Truebit enhancement of TrueBox or augmentation of it called the unchained index, which is a way of sort of taking method two and offloading the heavy lifting of method two, trying to put that onto a server. So down here, I'm just quickly showing you this server picture on the left-hand side. And on the right-hand side, you have what's going on in the local machine. This is supposed to be sort of the final solution, but the video starts off with a fully local solution, which is TrueBox, and then tries to upload it to onto this server. So I'm just gonna, I'll play that.
TrueBox builds an index of appearances of addresses as it scrapes each Ethereum block. Periodically, it creates a snapshot of the index, which we call a chunk, and an associated bloom filter, which is an order of magnitude smaller than the chunk. The API scans the index and informs the UI of which transaction details to give to the user. In Web 2, of course, the infrastructure is on a server, leaving the user interface in a browser. Server applications are not private, are not censorship resistant, they are not decentralized, and they are not trustless. They are not Web 3 native. And the problem is this query right here. For our submission, we wanted to see if IPFS could help TrueBox retain the benefits of Web 3 without requiring the user to run infrastructure. We left the API.
All right, and the last thing that I'll throw out here is that maybe we need a standard for data provenance, a standard way of retrieving data from upstream, a standard way of recording data downstream. So one of the organizers of this conference, Victoria, published a book, I guess, a month or so ago on archival methods pertaining to blockchain. So I think this is sort of a relevant topic called searching for trust. Anyway, I'll leave that up to your imagination. In any case, thank you all for your time, and I'm happy to open it up for questions.
Thank you very much, Jason. It's a great talk. Yes, you have some questions here. Do you want to read it or I can read it?
Let me take a look at the chat.
Do you consider Truebit optimistic rollup?
Do I consider Truebit to be an optimistic rollup?
Right.
If not,
really.
What
are the differences? In either case, can you highlight any foundational difference in how Truebit does fraud proofs as opposed to other projects like Arbitrum and Optimism?
I mean, Truebit is more about verification of those fraud proofs than the, I mean, you can use, Truebit can be part of an optimistic rollup. It can do the verification of those transactions, but usually, you know, the rollups are sort of like a mini blockchain unto themselves, which run all sorts of transactions. So yeah, I mean, I guess that's the simplest way I would think about it, is how you would, yeah, basically create the verification layer on layer one, which is also part of that roll-up infrastructure. That's the role of Truebit in this scenario.
So do you want to mention any differences with something like Arbitrum?
Yeah, well, I mean, Arbitrum has a similarity in that they are using, I guess, interactive verification, which is that verification game that we talked about earlier in this slides. But I mean, I guess the end user experience is quite different, right? I mean, Arbitrum manages state, and Truebit is a kind of a stateless system. So I mean, the experience of using Arbitrum is designed specifically to be similar to the experience of working with Ethereum, whereas Truebit is a kind of a very different model for that, for, I guess, consensus. Yeah.
Okay. Yes, so there are other questions. Yeah, so is the stakeholder participation in Truebit's crypto economic model is still permissionless? In other words, can anyone participate as a task giver, solver, or verifier, or would they need to request network access from some sort of network controller who would need to grant them participation to become a miner? Maybe someone in this chat can help answer this. So I guess you can answer this yourself.
I guess I'll take this one. So I think it's in our deployment on Truebit's deployment on Ethereum. Yes, it's still permissionless. Anybody can be the solver, verifier, task giver. There are no special addresses or anything like that in the network, and it's basically, I mean, completely decentralized for all intents and purposes. And so, I mean, everything that you do to interact with the Truebit on Ethereum has to go through a smart contract, and those smart contracts are, just operate in the way that they were designed to run. So that includes all the rules of the verification games, the commits and reveals of the solvers, the committing of deposits and paying out of rewards and all of those things. And of course, the verification game if it unfortunately has to take place.
Okay. So another question again from Jeremy. The motivation for dark pool was loud and clear, but I didn't follow how you do it. It's based on committing to trades and then revealing them later, or something different? Yeah,
it's not like the construction is not that simple. I intentionally didn't go into it, but there's I guess a custom multi-party compute protocol that's used in this specific instance, which has been, I mean, there is an implementation, so I can say that it works, but I think I also yeah, it's a kind of zero knowledge proof system that allows it to all the parties to get the assurance without revealing any of the order book at any time.
Okay, so I guess I just let people to unmute themselves. Ethan, do you want to unmute yourself and read your question, or you want me to do it? Ethan. Okay, so I don't hear him. So, hi, Jason. Let's talk about more future plans of Truebit. So, what we have already developed, what we have already development now and ready to use it. Is it
So,
theory or yeah?
so yeah, we do have a Truebit is in production on Ethereum mainnet and also the Goerli testnet. I touched on Truebit a little bit in this talk, but I don't think this is where we're going to go into product roadmap. It's not really the subject of this lecture. So, but I appreciate the enthusiasm, and I encourage you to stay tuned.
Okay, so the next question is, I guess, by Crypto Total Water. So I think we requested people to join the conference with their professional name, which hasn't happened here. But the question is on the Truebit website for use case. It states it can provide federated learning, performing machine learning and statistical operations. You had a slide on this in this presentation using a healthcare data use case. From my experience, the machine learning training process can be computationally expensive and lengthy in time, depending on resources. If I had proprietary ML training model and I want to test it with different data sets, however, each process is computationally intensive and lengthy. Could one theoretically outsource this process to Truebit miners? And I think it's a long question. Can the training model and training data remain private? Can one encrypt the WASM bytecode in the task and decrypt the solution once it is verified?
So I think the answer here is yes. I think I'd be interested in if someone is actually trying to do that. I would love to get more details of what's actually going to be done. I think this is a very interesting question and a great direction. So yeah. So anyway, yes, I think we can help with that. Maybe we could take this question offline.
Sure. Victoria, do you want to unmute yourself and ask your question or comment? Thank you for, okay. Thank you for mentioning my book, Jason. Your talk highlights the need for what I think we should call computational epistemology, to which archival science and blockchain can contribute. And for those interested in this, I had to say it in my book, so this is a reference to her book. Is there anything that you want to add, Jason?
Could you explain what you mean by computational epistemology? I'm trying to remember. There was another term in the book that I wanted to bring in here. I'll try to remember it while you explain that one. But yeah, what is computational epistemology, and how is it related to, I guess, what we put into this talk?
Okay, so I think everyone can unmute.
Okay. Hi, Ray. Yes, I wasn't able to unmute myself a moment ago, but
Okay.
yes, it was more just a comment than a question. But great talk, Jason, because I think what your shadows analogy really pointed out is something that I was really trying to point out and engage with in my book, which you've picked up on, and I thank you for that, which is really, how do we know what we know? And in a digital world, in a world in which we have developed AI processes for processing data and drawing conclusions, for example, of decision making and what have you, as you've illustrated, or just even what we can see in videos. We can't always be certain about that what we think we know is really what we know, because of what you have highlighted about uncertainty about upstream processes. So what I mean by computational epistemology is really what you're trying to define in your talk, which is what are the means by which we can prove computationally certain aspects of what we know. And really where I think archival science comes in is in how it has defined theoretically some of the aspects of and the stages of how we determine what we know. So things like accuracy, how that is different, I should say, from reliability, which is really about the representation of measurable events, as you've indicated in your sensor example. And then authenticity, which also came up in the NFT talk at the beginning of our day, which I think didn't receive enough of a highlight because the questions are not necessarily always around copyright. It's like and the experience that we were trying to achieve, by looking at a Mona Lisa or looking at an NFT, that has, when we know we've got close proximity to a private key, is really about the experience of authenticity and how challenging that remains in a digital world. So all of these questions are really about how we know what we know. How do we know that the thing or the asset that we're looking at is the thing that we're looking at? It's a kind of a variant, and I like your analogy of shadows, of Plato's shadows, his shadows in the cave, and questions about objective reality versus what we perceive, and whether there is an objective reality. So that, that gets us into some ontological space that, not important right now, but that certainly when we get into the weeds of these questions, we need to grapple with. So I don't really have a question. I have many questions, and would love to and encourage you to continue your explorations, and will definitely be, thinking a lot about what you've presented here today, because I think it's an area that deserves much more attention. So just, to thank you. That's all.
Sure. Thanks. Yes, I obviously your book is an inspiration, and I wanted to highlight one more concept that comes into the book that's kind of early on. In the beginning, you go through kind of a taxonomy of different kinds of trust. And I sort of view our notion that I presented here of distributed trust as an extension of what you called epistemic trust, which is basically what you just described. But I guess I missed the computational piece. I'm going to have to go back and
oh, that's kind of that's new, inspired by what you presented today. So I said,
okay, that's why I didn't. Perfect. So now we've come to the meeting point. That's I think that word is likely to come up again. I have a very strong suspicion. So it's not the last time you'll hear about computational epistemology. I love it. I just love it. Okay, that's great.
Yeah, and distributed, likewise, your concept of distributed trust, I think, articulating what is it that gives us trust in this distributed environment, and the point that I think is well recognized by yourself and by many, that we still have many centralized dependencies. So we are certainly not there yet. And when we have these, it creates all kinds of challenges for us, both epistemologically as well as operationally. So.
Yeah, I think probably what I said here isn't maybe so new to a lot of people, but just the fact that I put them back to back hopefully created a little bit more urgency around these issues, because I think it is a matter of seeing the world through the lens of computational epistemology that I wanted to convey in this talk, that there is this, I guess, right now I call it a special way of looking at the world, but 10 years from now, it's the way that everybody is going to see the world. And so I believe that this is, we are just taking a glimpse into the future, perhaps.
Great. So that was a very interesting discussion. Converging views, that was very nice. So there are a few small questions. So how far Truebit goes when it comes to being blockchain agnostic? Is it possible for Truebit to assist Bitcoin down the road, or?
We can assist anybody down the road. I think, I'm not sure this is the question you meant to ask. I mean, I think if you kind of read between lines in this talk, we've put Truebit in the context of things that transcend blockchain. Yes, we've clearly have a very well-defined, way of using the technology in the context of blockchain. But as we see this notion of computational epistemology, correct me if I'm wrong, epistemology is, this is the bigger world is computational epistemology. It's not Bitcoin. And that's not to say that Bitcoin can't be a part of the computational epistemology, but it's a small slice of it. And I think in some ways the blockchain is a great place to start. I mean, it's one of the few places in the world where the data is actually sort of incontrovertible. So you don't, the inputs are there. So in some ways you can get, there's certainly low-hanging fruit to be found in Bitcoin and these other types of networks. So I think it's a good question, and I think that I would say stay tuned. Let's see what happens.
Okay, so there are a couple of quick questions that I think that are left. I think, how does the adoption of Truebit on other blockchains look? Or maybe similar. How is the work going with Trick and Quadrants, which I don't know what it is?
Trick and Quadrants. Yeah, so it's going well. I think we'll have a sort of update there soon. And I mean, certainly, what was done on Ethereum could be, and Goerli testnet can be replicated on other chains as well. So if there's, specific applications that you're trying to reach on a specific chain, yeah, please feel free to reach out and let us know, and we'll see what we can do.
Okay, so the last question is on, again, difference between Arbitrum and Truebit. And the question is, what's the potential use case for Truebit that Arbitrum isn't well suited for?
Well, I mean, these are simple. I think I'm trying to see if maybe there's one even from the talk that we just did. But I think the dark pool example is a good one. I mean, for writing, if you're doing, well, there are two that we can pick out. One is machine learning type of examples. When we're talking about things that are not just using, oh, I ran out of gas. No, I'm talking about things that use billions or trillions or more of gas. Those are places where Truebit is maybe a better choice in the blockchain space. For most sorts of, do you need something? Okay, sorry. So with Arbitrum, I guess, you have more of an Ethereum experience. You can save money on gas at the sort of level of normal transactions that people are using. Yes, what would have cost $1 maybe costs a penny, that sort of thing. But I guess, when we're talking about machine learning examples or dark pool, where you have some code that was either complex or it was written in a language like, C or C++, and you just want to port it over. And I've seen people take code that was somehow they managed to munge it all the way into Solidity, and they rewrote it into, a WASM task for Truebit just because, it was easier to audit, when you don't have to overload so many variables and so forth. So yeah, I guess in short, the gas problem is multifaceted, right? There's the constant layer at the bottom, and then there's the asymptotic layer at the top for, absolutely enormous transactions.
So is that, am I right that, so there is a difference between privacy between the two? In Arbitrum, you have more contract privacy, but in Truebit, the computation privacy, but in Truebit, maybe you don't. Is that correct? Privacy of computation, I guess. Privacy is smart contract. Actually, it's a smart contract. No, the privacy of computation, actually, the privacy of computation.
So, yeah, I guess privacy there are a lot of different ways to, I guess, achieve privacy in this context, right? I
think the points, the smallest number of steps are done on blockchain, on Ethereum.
Yeah.
In the case of Arbitrum, maybe the number of steps in Truebit is more. Maybe this is more, open computation in that sense.
So I guess in both cases, the steps of the verification game would be written onto the blockchain.
Yeah,
but
okay.
So that's true. I guess I don't see how privacy is really comes into the picture here. It's
privacy of computation.
I see. So, well, yeah, I guess one of the, nice things about a verification game, regardless of which platform you're using, is that the individual steps don't really, if you're committing a bunch of hashes, you're not really revealing very much about the computation. So it can be kind of private. So in other words, if you started a task where only a few people had access to the inputs or whatever, you could privately play a verification game, get the same sort of, recording and provenance onto the blockchain without having to reveal the original states and you could get consensus without revealing, I guess, those whatever private pieces you would have had at the beginning. That's just one simple way of getting privacy. Obviously, there are other ways you could do it, like you could use Truebit to verify a bulletproof, for example, which is another zero knowledge proofs are sort of originally, even though people think about them now today a lot for scalability, they were originally designed as ways of getting, private, proving certain facts without revealing inputs. And so, in certain cases where the verification time is longer and you wanted to do it on chain, you could use that with Truebit, for example. So bulletproofs is a good pairing. Anyway, a couple ideas.
Thank you. Yep. Okay, great. I think
Sure.
Thanks very much for you spent a lot of patience to answer all these questions. Everyone excited about your work, so that's great. So thanks very much.
Thank you. Yes, I'm glad we got to go through many questions, and I know we're a bit over, so I will we can wrap it up here. But looking forward to the rest of the conference.
Thank you so much. Thank you so much
Okay, thanks, Ray.
for the talk. Yeah.